So actually, I have to introduce my colleague Jianmin Zhou, who put more effort on this to come up with the optimization algorithms. He was not able to travel today. I'm actually presenting his work here. So we have actually 3-stage optimization have done to achieve the demand response. So this is the Siemens way of adaptive intelligent demand response mechanism. Here, so this is actually a base load of the building, and so here, we have here, it shows the HVAC consumption based on the prediction for tomorrow's weather. But on the DR day, and so we actually based on different behavior of the building, different occupancy, different activities in the building. The consumption was not as predicted, but the real consumption was up. So during this time, what happened, if you look at the overall load, and there were some still peaks which shows up here. So this is all these kind of peaks we use instant load reduction, such as plug load and also central lighting. So that is what we have explained earlier. So we use the negotiation approach to come up with that. So optimal HVAC control for demand management. So the objective function is minimum energy cost or consumption, peak load, or the cost of comfort loss. All these factors were considered to come up with the right strategies. The decisions are involving set points, zone, AHUs, chiller temperature set points, pressure as well. And also operation mode, heating or cooling. And when we are pre-cooling, we don't want to building to go into the heating mode at any time. And we can use mechanical or natural ventilation wherever it's possible. So the constraints are always we need to consider to come up with the right strategies. Sorry. The constraints always we need to consider. Physical constraints. Thank you. Physical equipment constraints and also the limits that are allowed to change. So all these things have to be considered to evaluate the best strategy for this building. It's actually model-based predictive control. In the industry, in order to come up with the right strategies, mathematical model of a building and also HVAC system is used to come up with the right strategies. But it's really a complex mechanism, and if you wanted to commercialize and implement in the real-time buildings, there's going to be too much effort. It takes time to come up with the right strategies. So with that mathematical models, we also have some challenges, such as accurate modeling of the building and its thermal behavior, and prediction of climate and internal heat gains is inaccurate. So we have to, we don't know how is occupancy behavior all the time. It can change dynamically. And also thermal comfort is difficult to define quantitatively. So with these two, what we have done was we came up with a 3-stage approach. The first stage, we come up, we evaluate all the strategies. The first, this is the offline. That means we evaluate first strategies, and the second stage we configure them in the smart energy box. And then, so during that time, smart energy box uses the real-time weather and the strategies that were already evaluated in the first stage, and then it takes the best strategy. In the third stage, even if you have a still load to reduction, it's going to be contracted to the instant loads, such as plug load and also central lighting. So for this project, for the Berkeley, we identified 19 weather patterns for the Berkeley weather, and we took from the last 10 years of historical data, and we come up with all these patterns. And for these patterns, we designed the strategies, HVAC strategies, and those involves zone temperature reset and supply temperature reset, supply fan static pressure, but we could not control here, but even though we have used that for the evaluation, and also VAV minimum airflow requirements, ventilation. So we have used another mechanism as well as condenser water and chilled water supply temperature set points, but we did not implement for this project. But we have evaluated those, we have used them for the evaluation as well. This is actually one of the pattern. It's a hot weather. When we use the energy plus model from LBNL and the strategy that we have adapted, then we were actually seeing we were seeing the energy consumption shows. I mean, here the base load, which is 863. If you just control the air handling, we were gaining around 6%. If you use both air and water, we saw like 14% in the reduction. And in the second stage, the first stage, all the strategies, like we have identified 19 candidate strategies out of 5,250 strategies that we identified. So we configured all of them. Smart Energy Box, it uses the real-time weather data. And then it uses all strategies and simulates using Energy Plus, picks the best one. So whenever the day starts, it starts applying on the building. So next, I'm going to hand over to my colleague, Siyuan Zhou. She's going to explain the stage 3 optimization.
Thanks, Prasad, for the explanation for the previous 2 stages. And the third stage is about contracting the power reduction goals that we cannot meet with only the HVAC system. So we distinguish between the HVAC system versus the lighting system and the other plug loads with gateways. And the reason is that they have different characteristics. The lighting system and the plug loads has a feature, which means that they can react in real time, and their power reduction is corresponding directly to your control command, which means I turn off a light, I shed 60 watts. And that's not the case for the HVAC. That's why we want to put those systems together to contribute to those portions that the HVAC cannot meet when we are doing all the pre-configurations, pre-optimization. And we can do that in real time. And the way to do is that during the DR event time, for example, 2 hours, and we divide them into the 15-minute interval, and every 15 minutes, the Smart Energy Box would read from the building meter and compare that with our demand response goal. And if we still need to shed something else, then we go to the lighting and the plug loads. And every time when we need to shed anything, then Smart Energy Box would start the negotiation. And all those agents that would representing the plug loads and the lighting system would react according to their own circumstances. And they can agree to apply the control or they can refuse. If they agree, then they send some information back to the Smart Energy Box, and the Smart Energy Box would do his optimization and then send back the goal at the end. And I would go into detail later. So for the, especially for the plug loads, we divided the optimization in 2 levels. One level is between the Smart Energy Box and the gateway agents. And the second level is from the gateway agents to each of the appliances. We define a cost function for each and every appliance. That cost function is like the utility function in economics, which represent the relationship between the power consumption to the comfort level. And after the gateway get those cost functions from each and every appliances, he would calculate one cost function for all the appliances. Then he would submit that cost function into the SEB. Here are some examples of the cost functions at the appliance level. Then this cost function was calculated considering the relative importance, which was set by the user. And it would also consider the maximum power of this appliance. And how many points of the cost function would be decided by the control levels that we can apply onto this appliance. For example, if it's only on and off, then we only have 2 points that is possible to be controlled. But if we can dim a light, then the cost function would be continuous. And the whole procedure is that when the SEB asks for, okay, I need to shed more power, and then the gateway would get those cost function information from the distributed loads, the plug loads, and then do its cost function calculation to calculate one cost function for all the plug loads. And he would submit that to the SEB, and SEB would collecting all the cost functions from all the gateways and the lighting agents, and then do his optimization to send back one power reduction goal for each of the agent. And then the agent would then do his optimization to decide which of the appliances he would like to turn off. So that's about it. Is there any question for me or Prasad? Yes?
I just noticed a lot of office buildings or small, medium business customers would be on a peak day pricing type demand response program.
Yes.
Where they just pay extra money per kilowatt hour, but it doesn't matter what the demand is. So it's like over 4 hours, 2 to 6 p.m. on a peak day pricing event day. They will pay more for electricity based on the kilowatt hours consumed over that period. But it doesn't really matter how much kW peak they use. So it's a different, I mean, there's demand response programs that charge or give credits based on kW.
Yes.
But most of the buildings, I believe, small, medium businesses will be opting for a peak day pricing type demand response.
So Charlie, isn't it about 80 cents a kilowatt hour for 4 hours?
Yeah, it goes up to, depending on the size of the customer, it could be another $1.20
Right, up to $1.20. So it's $1
cents.
for a kilowatt hour. It's sort of the same thing for those 4 hours.
Right, it's constant over, so it doesn't matter. In other words, they could go up to 1,000 kW for a minute, or 15 minutes. But over 4 hours, they might have 100 kW. But it doesn't matter if they reduce kW load, really. It's just kWh that.
But it's an hourly. They get charged for every hour. And for those, so say it's 2 to 6, I think it is.
Okay, right.
So from 2 to 3 o'clock, they're paying $1 a kilowatt hour.
Well, from 2 to 6 p.m., right.
So,
exactly.
So for the first hour, it's $1 a kilowatt hour. The second, so it's essentially for those 4 hours, they want to reduce as much as they can for the entire 4 hours. That's
Exactly, that's what I'm saying. It's an average value over 4 hours instead of an average value over 15 minutes, which I think what you've got here. So it's something to keep in mind that there's 2 types of, I guess, strategies for participating in demand response in California. You can either do real-time pricing or peak day pricing, or you can do,
Yes.
the KW time.
Right.
So
I think that is a very good comment on our
it's just something to
strategy.
keep in mind.
Yes, I think our strategy was designed for one type of demand response, and for the other type, we can also come up with something that deal with the kW hours. Then that would make more sense than this one.
Yeah, that would be good.
And
Okay.
these 15 minutes, you just what we are using for the optimization. It's going to be happen for the 4 hours, but every 15 minutes it's going to plan for every 15 minutes it's going to plan. So that means we have actually 10 rooms in the office. So maybe first 15 minutes, room 1, room 2 can shed some load. The next 15 minutes, room 1, room 2 has some meeting, and room 3, 4 they can actually shed. So that's the reason why we kept shorter intervals to negotiate inside the building. So even though we receive 4 hours peak day pricing event, so we are actually asking the agents, so a short-term commitment.
That makes sense.
Yeah.
So if they're shedding load and never using that load again, that's different than if they're shifting load to say, half hour later. what I'm saying is if they're on a peak day pricing, demand response type program approach, if they're shifting load, they're still going to pay the same amount for the electricity. But if they're not using the electricity, they're going to save a bit, like Mary Ann said, $1.20 or so.
Yep.
Like KWA. This will work, but mainly I think if they're not using that electricity. So what you described here is more of a, I think, a permanent load. It's a continuous load minimization program.
Yeah.
Which is really good. That's really good. Because they can use it all year.
Thank you.
Yeah.
Good question.